All right. So we're going to go ahead and get started in just a second. Lisa, are you there?
I'm here. Sorry, just getting used to Zoom.
All right. Well, everyone, good evening. So this is going to be our October meeting for CGS. So again, just like the last meeting, there is a chat function within Zoom here. So at any time, if you guys have any questions, feel free to use that chat, and either we will, ask Lisa to talk about it during the meeting or afterwards. So feel free to use the chat at any time. And so with that, I'm going to do a little bio for Lisa. So Lisa is currently working as a geologist at Era Energy, where she has been since 2012. Lisa received her PhD in geological sciences from USC in 2012 and her MS in geology from CSU Los Angeles in 2006. She is also a part-time professor at geophysics at CSUB. And so with that, here's our October speaker, Lisa Alpert.
Thank you. Thank you guys for having me. I was looking forward very much to heading to Ventura and staying there overnight and giving that talk in March. I was very sad, but I appreciate you guys having me back. So I'm going to turn off my camera because I'm going to be looking at my big monitor. And I don't have a great internet connection. So thanks again for inviting me to talk here. And let me just turn this camera off and then we'll get going. So today we're going to be talking about some work that I did during my PhD at USC. Can everyone, if you can't hear me, someone just interrupt, but I'm talking into my AirPods, but hopefully it works.
Yep, we can hear you loud and clear.
Good. So I did this almost 10 years ago, but in my defense, subducting slabs haven't changed much since then. I also don't get to share much of what I do at work these days. And since many of us work a bit higher up in the strat column, you might find this interesting. So the work I'll be talking about involves how we can use observational data to make inferences about deep mantle processes. And what we're talking about, the mantle, we're talking about obviously the layer of earth beneath the crust and above the outer core. So much deeper than you're used to seeing probably, and much more homogeneous. So what we're going to do is talk about today is how slabs interact with this upper mantle and the lower mantle. The reason why we're looking at that is because subducting slabs coupled to the motions of surface plates exert a pull force that contributes to global plate motions. In the upper mantle, these slabs also induce a flow, and density exerts tractions on the base of plates that further contribute to surface motions. So together, these forces are acting to make subducting slabs the main driving force for plate tectonics. However, our fundamental understanding of what happens to subducted slabs as they enter the upper mantle at convergent plate margins is limited because we don't have a lot of signatures of the process. So we have laboratory numerical modeling of subduction dynamics, and they've advanced our understanding. But the key for validating these models is to compare them to scarce observational data. So here we're going to look at earthquake data, and we're going to use this data to infer some constraints on the rheology of the subducting lithosphere in the upper mantle. So here you're just looking at earthquake distributions, and you can see obviously the plate boundaries. This is what we're calling source seismology. It's simply earthquakes or seismic strain release. Deformation within subducting slabs in the upper mantle is accommodated by seismic strain release. So seismicity has become the main observational tool in understanding subduction dynamics. So the talk today is going to be in three parts. First, the overarching goal is to show that numerical models, even though they're models, can help you understand global and regional phenomena. It's going to be, you can use those global inferences in finer regional models to enhance your resolution or add more detail. So I'm going to talk first about the deformation state of slabs that we identify using our quantitative data. we're going to talk about how I use that information and compare it to the results of global modeling, and then how I use the information from the global modeling to bring it to a regional place and actually attack a real world problem that has surface deformation. And I'm going to talk about the band of sea. So the first part is what the data is. And what we're looking at, of course, is seismicity. And we're looking at seismicity only within slabs. So seismicity in the slabs is caused by planar faulting and by buoyancy forces from the density contrast. The earthquakes within the slabs identify a planar zone of seismicity called the Wadati-Benioff zone. These earthquakes in the Wadati-Benioff zone can be as deep as 670 kilometers, which is essentially the depth extent of the upper mantle. So here I'm just showing you some work from Isaacs and Baranzaghi from 1977. They're inferring the geometry of the slab based on the distribution of earthquakes with depth. So what seismicity is doing, it's telling us how something is deforming by the pattern of seismic radiation that's created during an earthquake. So this is what you've seen as a focal mechanism or a beach ball. And it tells us in which direction the rocks are getting pushed or pulled, meaning that in between them, there has to be a fault in this particular case. So this is telling us the pattern of deformation, and then we can infer the deformation that's occurring in the slab by using these types of solutions. So the early work would use these focal mechanisms or beach balls to infer how slabs in the upper mantle were deforming by looking at the orientation of these compressional and tensional axes of the focal mechanism with respect to the slab geometry. So they can say that if the compressional axis is parallel to the slab geometry, then that slab is undergoing compression. And if the tensional axis is parallel, then it's undergoing extension. So this gave them, in this particular case, the work of Isaacs and Molnar in 1971, they compiled focal mechanism data from these subduction zones, 24 of them actually, and they identified these general patterns of deformation within slabs. And what they saw was that for slabs that were reaching the lower mantle, they were undergoing compression indicated by an open circle, and they were generating extension for the most part at intermediate depths, indicated by the solid black circles. The line is inferring the slab geometries. And what they said was if the slab reaches the lower mantle is increasing in strength as you go down, and then the lower mantle is high strength, so it's generating compression at the tip of the slab. And as you go up the slab, you have less of a viscous force, but you have a buoyancy-driven force that generates extension. However, you can see from this picture that the extensional deformation, the intermediate deformation state is fairly complex. But we're going to redo this work with a newer data set. So back in the 70s, Harvard and USGS came up with the waveform modeling, which generates a centroid moment tensor or CMT solution. This moment tensor is analogous to the strain tensor, which represents deformation of a body. So we describe the tensor by the trend and plunge of the principal axes, the compressional, the tensional, and the null, just like a beach ball mechanism. We don't force it to be on a planar fault, but that's for, we can discuss that later or some other time. But you've got three eigenvectors, and you've got the three principal moments or the eigenvalues, which tells us the magnitude of the deformation away from a point source. But when you see a beach ball diagram on those USGS maps after an earthquake occurs, they're basically this double couples moment tensor solution. They take the moment tensor and they force it to be on a fault plane, and they make a beach ball. It's not technically, they call it a focal mechanism, but the actual data is coming from a CMT. So what we do first is we're going to look at over almost 5,000 CMT solutions, and we're going to sum them up or put them in a histogram with depth. And we're going to look at general patterns. And all we're trying to do here is to come up with some definitions of what's intermediate and what's deep. And when we look at these 5,000 CMT solutions, we notice that there's a precipitous drop off of activity around 350 kilometers. And then we start increasing again from 350 to 700. So we just use this to say that 100 to 350 is going to be what we're going to call intermediate, and 350 to 700 is going to be deep. We do not use earthquakes from 0 to 100 kilometers because we want to avoid events that might be associated with plate boundary stresses. So now we just have some definitions, just for reference. The dashed line marks the 410 and 660 olivine phase transitions, which is just something I tested in these models, but you're not going to see results of that here. So here's just an overview of the kinds of cross sections that I chose. I tried to mimic the work of Isaacs and Molnar to the best of my ability, given the information I had. And what you're seeing here is the global compilation of all the moment tensors with their associated strain orientations and their hypocenters. So the black circles here are the moment tensor solutions in this particular subduction zone. The green vectors are the orientation of the compressional axes. The red circles are just all of the hypocenters for that region. The background is P-wave tomography. So basically, if it's blue, it's cold, and we infer that's our slab. If it's red, it's warm upper mantle material. So that just gives us our bearings and shows us the kinds of compilations and the amount of data that we have in these different subduction zones. So what I did next is I took the 24 subduction zones that I wanted to compare to the work of Isaacs Molnar that had enough data that I can make some inferences. And I did a similar processes, except I used the moment tensor solutions, of course. So here you're seeing summed and normalized moment tensor solutions in each subduction zone. The black lines are showing you the orientation of the slab inferred by a polynomial fit to the earthquake data. And that means not just CMT, that means all of the hypocenters. The circles are the actual CMT solutions. The vectors slicing through the circles are the orientation of the compressional, I might start saying P axes, and the color of the circle represents the magnitude of the extensional component of the tensor, measured according to the slab dip. So if it's blue, it's undergoing compression. If it's red, it's undergoing primarily extension. Anything in between is colored in between. So we see from this, very similar to Isaacs and Molnar, if a slab reaches the lower mantle state, though, it's still more complex. And that is what we're going to focus on for the rest of this part, because it's pretty easy to match the data if everything is doing the same thing. But if you have a deformation state that's more ambiguous, then that's really what I want to focus on. So here you're looking at the 24 zones, and you're seeing the intermediate depth deformation state indicated by the color. So again, red is extensional deformation at intermediate depth. Blue is compressional deformation, and everything else is somewhere in between. And these are just representing the segment of the subduction zone that I used for the comparisons. So of these 24 regions, 13 of them actually have deeply extending seismicity, which I actually used in the numerical models. So the names of the subduction zone here, how many segments I used for comparison is in the number in the parentheses. If it's italicized, that means it doesn't have deeply extending seismicity, or it's ambiguous with the orientation of the slab geometry, so I didn't use those. So now I have a total of 30 segments. The blue lines here are the Novell 1A plate boundaries that I used for my model. What you're going to see is keep focusing on this intermediate depth extension on the east here and compression primarily on the west. This pattern of subduction polarity being tied to intermediate depth deformation state has been invoked by plenty of people. what they're focusing on is, one of the things they're focusing on is the net rotation of the lithosphere with respect to the upper mantle, which I'm going to talk about that a lot in the results section. I'm not going to talk about it here, but it's something that I was able to test with this type of flow model. So keeping that in mind, now we know the deformation state from the actual data. And now I'm going to do the numerical modeling portion of it. So what I'm going to start with in this section is a 3D sphere. I put a core in the center. Between the core and the surface, I have an upper mantle material of a specific viscosity that I can change as I run through the version. I don't show the viscosity here, else you wouldn't see anything. I have the plates at the surface. I break those plates up according to the Nouvelle 1A plate motion model. And I start pushing those plates using converting the relative plate motion model to absolute reference frame. And then I stick these cold slabs into the upper mantle. These cold slabs are going to generate buoyancy forces. The surface velocities are generating a surface flow. And a couple things are going to happen as soon as I take a snapshot in time. And what's going to happen to the actual model is that the surface velocities are going to propagate into the upper mantle along the convergent margins. The slabs themselves are going to generate stresses, and they're also going to feel that flow from the surface plates as stress, which means that throughout this model, I'm going to have the largest amounts of stress within and around these slabs. That's where the stresses are going to be greatest. I'm going to have the input is my buoyancy and my viscosity and my velocities. The output is going to be those particular stresses in those slabs. So here I've gotten rid of the minor stresses caused by the surface velocities only, and I've isolated the stresses within the slabs according to the same profiles that you saw before. I took those stresses because stresses come out as a tensor. It's analogous to our strain rate tensor, which we get from our beach ball diagram. I convert my stress tensor to a beach ball diagram, and now it looks like I'm comparing apples to apples, which essentially I am. So I'm going to take the output of this model in the form of stresses and look at the orientation of the compressional and tensional axes. So a couple assumptions that usually I get asked about that I'm going to cover right now is that I'm treating the Earth as a continuous medium, and I'm saying that on long enough time scales, all the deformation within the Earth can be considered viscous. You just have to accept that so you can do the math, okay? So I'm just going to solve my conservation equations. Conservation of mass says that everything I put in the box, in this case it's a round box, has to stay in the box. And the conservation of momentum says that my buoyancy and viscosity forces have to balance. So everything's balanced. It solves the equations and it outputs what stresses I would need to balance the input that I gave it, okay? So for every iteration of the modeling, my output is going to be a cross section through a region. The background you're seeing here is colored in this particular case by viscosity. So white means that there's no viscosity difference between, I'm sorry, there's no viscosity change. But here where it's gray, there's probably a 1 order of magnitude viscosity increase. There's probably 10 to 100 viscosity increase in the lithosphere. I'm just showing you an example of what we're going to be looking at. And then I'm showing you an increase in viscosity in the lower mantle. So this is depth on the Y and the distance across the subduction zone on the X. These blue solutions, I'm just showing you, instead of the beach balls, I'm showing you the orientation of the compressional axes of that stress tensor that I got from the model. The red axes is the compressional axes of the stress of the CMT solution, the actual data point. And the green is the orientation of the compressional axes from the stress tensor matched to the location of where the CMT solution is. So we're going to be focusing on the green compared to the red. And the quantitative part of this is that I'm going to actually look at the angular 3D mismatch between the orientation of these axes. And that gives me a number. So that number is calculated for 100-kilometer depth bins where I have data. The lower the number means the difference between these two axes is smaller. So I want small differences. So I'm calling it Misfit, but I want low numbers for this Misfit, meaning that the model produced a match to the actual data. I sum these up and get an average for this particular transect. This is how many solutions I compared. The regional Misfit is that particular subduction zone. So if there's 4 transects in that one subduction zone, this is how it performed regionally. And I also calculate how they have performed at a global scale. So that's what you're going to be seeing in the next comparisons. So I tested over 500 models. I'm not going to show you, obviously, all of them. I don't discuss models that don't have a significant effect on the orientation of the stresses. I'm going to show you the ones that have the greatest effect. And those are going to be 3 different parameters. One is how I push the plates. The other is how strong the slab was. And the last one is how strong the lower mantle was. These are all relative to the background upper mantle strength. So those are the only ones I'm going to talk about because they had the most impact. Okay, so the first one is how I push the plates. So I told you I invoked a surface velocity by pushing the plates according to a relative plate motion model. And that generates my initial velocities that get propagated into the upper mantle. So a relative plate motion model, once you use it in a quantitative way like this, you have to hold something fixed and have it be an absolute reference frame. Depending on what you hold fixed, you are not going to be able to accommodate all of that relative plate motion in an absolute reference frame. You get some extra motion, which is essentially intraplate deformation. There's 2 things I can do. I can say, I don't want any net rotation and take it out. And that's called an NNR or no net rotation reference frame. Or I can allow this net rotation to happen. And depending on which kind of reference frame you use, you can get more or less of this net rotation. So I use the end member. So it's called reference frame. It's called HS3. And that generates the largest amount of net rotation. And this net rotation is literally the motion of a lithosphere relative to the upper mantle. With everything held constant and just pushing plates, you're going to generate a westward net rotation of the lithosphere. That has nothing to do with slabs or anything. Okay, so again, 2 end member reference frames. Hotspot or HS3 generates a huge amount of net rotation, and NNR, which is no net rotation. And the reason I'm doing this is because Doglioni et al. In 1999 said, I think this net rotation of the lithosphere is the reason why we see this intermediate depth deformation complexity. So in the east versus the west, because of the flow of this of the lithosphere with respect to the upper mantle. So this is a theory I could test by imposing this net rotation in my models. And what they're saying is that depending on the polarity of the subduction zone, if you are an east-directed subduction zone, you are going to go along with this relative asthenospheric flow, and you're going to generate additional extension on east-directed subduction zones. But on the west, you're going to generate compression because you're going against this relative flow. So pretty simple and something I can test and something that seems to work with what I've already shown, rotation pattern. If you take the globe and you flatten it out, and you can see that over here in the altiplano, you've got east-directed subduction zone with extension in intermediate depths. And here in Japan, you've got mostly compression at intermediate depths. And it seems to follow the pattern of the net rotation of the lithosphere. Okay, so now I'm just going to show you one slide of what happens to my stresses when I impose this net rotation. And what you're looking at is on the left side, there's a west-directed subduction zone, the Corral Trench in Japan, near Japan. And on the right side is an east-directed subduction zone, Sumatra. And on the top, I don't impose net rotation. And on the bottom, I impose the highest amount of net rotation. The things you want to focus on is the red is the actual CMT solution, at least the compressional axes. The green is what came out of the model. When I don't have net rotation in my model, in a west-directed subduction zone, I get extension at intermediate depths, which is, we saw that happened, which obviously doesn't match this red, which is the actual data point, which suggests that the slab's undergoing compression. When I impose a net rotation, my actual solution rotates into compression, which does a much better job of matching the actual data point in west-directed subduction zone. So I go from a regional misfit of 36.9 to 26.8. It's pretty good. Again, at the east-directed, they're undergoing intermediate depth extension, as inferred from the actual data in red, but my model can't produce that extension if I don't have net rotation. It shows compression for the most part. Once I generate this net rotation, I rotate my vectors into extension and thereby match my original data better, reducing my misfit considerably for east-directed subduction zones. So it works, it's plausible. I was able to match the data. I cannot match the data in the intermediate depth nearly as well without having this net rotation. I also evaluated how much net rotation I had. So I reduced the HS3 net rotation by 25% from 25 to 100, and I needed all 100% of HS3. So interesting find. Okay, the other thing I'm going to look at is slab strength, and I'm just showing you the Marianas Trench. From left to right, I'm taking a slab that is 10 times more viscous than the background upper mantle. Again, the red is the data point. The green is my stress tensor solution. You can see that you've got normal intermediate depth extension. You've got deep compression. In this case, the lower mantle is 10 times the upper mantle for all of these cases, because I'm only looking at increasing slab strength. As I move to the right, I'm increasing the viscosity of the slab relative to the mantle 100 times and then 1,000 times. And what you're doing is you're basically starting with a simple buoyancy-driven model where a slab is undergoing extensional deformation basically from the buoyancy force of the slab entering the upper mantle. And once it hits the lower mantle, it starts experiencing compression from the stronger lower mantle. As you increase the slab, you start rotating these stresses into more compressional. So it's more of a viscous bending dominated system than a buoyancy dominated. Eventually you get to the point where the entire slab is undergoing compression, which you can see does not match the data. So your slab cannot be this strong if this is the kind of match you're trying to get. So something between 10 and 100 looks like it can do pretty good. You look at the misfit in the regional sense and it's pretty close. And then you can go ahead and compare it to your global misfit to see how it does across the world. Now I'm going to increase the lower mantle strength. And that's basically taking this puerile trench, and you can see that there's no increase in viscosity in the lower mantle here. It's the same as the upper mantle. Over here, I've increased the viscosity. I think this is probably this is 100 times increase. If you don't have that lower mantle strength increase, you can't generate compression. It's still undergoing extension according to these green lines in the model. In reality, it should be under compression. So I have to have some kind of lower mantle viscosity increase to generate compression at the slab tip. That's not very surprising. We're going to show you a compilation of the data to show you which models performed in a global sense the best, and then we'll be done with part one. So what you're seeing here is misfit versus the slab mantle viscosity contrast for different lower mantle strengths. It's a lot of information, but basically it's a third of my PhD in one slide. If you take no net rotation reference frame, that's the solid lines. The lower the misfit, the better the model. So you're looking for that sweet spot. So for no net rotation, you always perform, for the most part, worse than if you impose net rotation. So we said you have to have some kind of net rotation, because it gives you a lowest misfit in just about all cases. And something in this range seems to be where you want to be. So the slab mantle viscosity contrast is 100 times. The lower mantle viscosity contrast is 30 to 100 times. You can keep getting finer and finer here, but there's no sense in doing that in a global model. You'd want to take this and you'd fine tune it in a regional model. But this is basically the overview, and that gives us some constraints on how strong our slab and our lower mantle has to be. And then you look at that in kind of a regional distribution of misfit now. It's not extension, it's just misfit. So red means it's not matching very well. Blue means it matches really well. So still complexity, but for the most part, you can find a model that gives you the lowest misfit and say that for a global model, it does the best when you have an HS3 reference frame, that the slab is 100 times the upper mantle and the lower mantle is 10 times the upper mantle. So that just gives you some constraints on a global sense. So we used that we published a couple of papers to talk about these summed CMT solutions. I published what you just saw, and it led to some other things. But the most important thing it led to is the last part of this talk, which is about how you can take that information and at least you're not starting from nowhere. You have some idea of the strength of these things, whereas before you really didn't know what you were going to put into in a regional model. So the last part of my PhD, I took my regional work and applied that knowledge to the band of sea. So I was trying to look at slab tearing in the band of sea and what could be causing the tearing of slabs. And this slab tearing can be responsible for some of the surface uplift patterns that you see along the Banda arc. So this area is extremely complex. It's the confluence of 3 major tectonic plates. You've got Southeast Indonesia. It's one of the most complex geological domains on Earth. On the west side, you've got the Indian Ocean lithosphere subducting under the Java Trench. On the east, you've got the Australian continent colliding with the Banda arc. Between them, you've got back arc deformation, volcanism, gaps in volcanism, intermediate depth seismicity, asymmetric surface uplift patterns. It's a very complex area. Right now, it's in a continental collision phase with the Australian shelf, with some mixed continental oceanic plateau, where the Scott Plateau is colliding all along the eastern end of Java. So extremely complex, but the surface uplift patterns led them to think that there might be something going on underneath in the mantle that could be explaining these. Also, the seismicity, of course, is complicated as well, but what the thought is that the seismicity and the surface uplift and the deformation patterns and the volcanism could be explained by the collision and underplating of this Scott Plateau on the edge of the continental shelf, going into the subduction zone ahead of the Australian shelf, underneath Sumba, and it's leading to back arc deformation, activation of thrust faults, and then we get the Australian shelf coming in later. So a lot going on, but this was what some people's thoughts that could explain the uplift patterns, because as the Scott Plateau promontory collides with the Sumba, you get different uplift patterns to the east and to the west. So these surface uplift rates, they are interpreted as a response to changes in the convergence, and the isostatic rebound caused by a possible deep slab detachment or delamination of a lithosphere from the slab. So this variation in the rates have been attributed to the collision initiating at the eastern edge of the Banda arc and propagating westward along the shelf. The islands of Savu and Rote experience rapid uplift at different times, suggesting it's caused by this the collision of the Scott Plateau. So they said, can you do some 3D modeling that might help us explain this? And I said, of course I can, because it looks really fun. They also saw that seismicity, excuse me, sorry for just a second here. Okay, I'm here. The seismicity and the tomography suggests that there's possible areas where you're not seeing intermediate depth seismicity, and they're saying that that could be caused by these gaps in seismicity could be caused by detachment of the slab. So here you're looking again at the P wave tomography where cold is blue, indicating that there's slab material there, and red is the warm mantle. So they noticed that these gaps in these warm areas suggested that there was no slab there, and the lack of earthquake also indicated that there might be some gaps in seismicity. In this case, it's called they recognize this as the wetar seismic gap under Timor. So with all of that, what we were trying to do is we can generate lithospheric tears in slabs in response to subducting buoyant continental material along the trench, along the margin. How much gets subducted of that continental material gets subducted in the boundary is what controls that. And does the morphology of the impingement have anything to do with the tear generation and propagation, and how you can apply this to the band to sea? So what I did was I made up some continental morphologies. I had embedded a continental material within a subducting oceanic slab. This is now a box model. It's a regional model because it's a fully dynamic model. So I wanted to explore how these different morphologies would affect tearing or slabs at depth. We're also going to test different buoyancies relative to the slab and see if we can look at directions and propagation of slabs. So the first thing I wanted to establish is that if you don't have continental material embedded in an oceanic slab, that you don't generate slab tears. And this is just showing that for, don't worry about the power law versus viscoplastic. I tested some power law models. You get the same results, you just get it faster. But this is just showing a thermal slab, just a cold slab, and you can subduct it as long as you want. You're not going to generate a slab tear. Once you put in continental material, you do generate a slab tear when that buoyant continental material enters the trench. And slab tear here means that I just have very little temperature difference between the background upper mantle, because I'm not actually, it's a ductile deformation, so there's not technically a tear. It's just when it's equilibrated with the background upper mantle temperature, that's when I infer that it's been torn. So here you're seeing if you increase continental Rayleigh number compared to the thermal Rayleigh number, that you're going to generate a slab tear. So the more buoyant it is, the more the deeper it's going to subduct into the trench. So I'm sorry, the less buoyant it is. So if it's consistent with the upper mantle buoyancy, then the continental material is just going to go into the upper mantle and get subducted, shown by the black in the side here. If you increase the buoyancy contrast, you don't subduct the material as deeply into the upper mantle. And here's a movie showing what happens when you increase continental buoyancy. So increasing to the right, the purple up here is the continental material. You can see, of course, you're generating a slab in every time, but as you increase the buoyancy, you subduct less of the continental material. So the next thing I want to do is to look at what the shape of the continental material has to do on the generation of tears, and not only just the first tear, but sometimes the second tear. And what you're going to see is that depending on the morphology of the material or the continental material, you can generate a secondary tear. And I'm going to show you a movie about 4 different morphologies. The shape of the continental material is shown in the inset. And you're going to be seeing some of these cases will generate secondary tears that can propagate along the margin of the continental material. And there's your secondary tear being generated. So what that means in our world is we tested a bunch of different morphologies, but we're trying to compare it to what we saw in the data. So we found that we liked our tear that's going to propagate in an opposite direction to the initial tear. So this is what most relevant outcome is the extended continental margin generates the secondary tear. And these propagate along the margin in a direction that's controlled by their morphology. And there you see it. That's the Scott Plateau model. And now we're going to compare that model to the data. So if we look at looking to the north now, you see the wetar seismic gap, and you can see that that's generated by the continental collision of the Australian shelf. The secondary gap is generated by the impingement of the Scott Plateau. So we say that the Australian shelf collides with the band arc. It generates a west propagating slab tear, evidenced by the wetar seismic gap. And then before the tear completely detaches the slab, the collision of the northward protruding Scott Plateau and Sumba generates east propagating slab tear. Between the tears, the oceanic material remains intact. This generates a typical type subduction and the related earthquake patterns beneath the Sabu Basin. So our model D, with the northwest protrusion analogous to the Scott Plateau, generates slab tear propagation similar to distribution of the seismicity. We also suggest that there's a significant gap in seismicity beneath eastern Java, and we think that's the consequence of an additional slab rupture. There's another piece of material coming in under Java. So you can see that we can apply some of the global work that we did to a regional problem. We can enhance that regional problem with more information, higher resolution. In this case, we made it dynamic, and we're able to make some inferences about what can be happening beneath the band of sea that could be explaining the surface uplift patterns and the deformation state and the volcanism. So we also learned that buoyancy contrasts are going to control the generation of slab tears, that you have to have continental material, that you can generate tear patterns as a function of the margin morphology. The tears could propagate in either direction based on that morphology. And we think that the Rheology rise is coming in beneath Java on the east into the trench and might be responsible for an additional slab tear. So with that, we were able to use these movies and submit a request, NSF grant application, which they're currently still working on. So they're bringing this back to life. They got almost $1 million to go study more of the surface uplift and how it relates to the deeper slabs, and still working on it to this day. So they also have endless amounts of abstracts from all the different techniques that they're using in the seismometers that they're deploying in the band of art, generated from looking at this kind of 2D, I guess 3D dynamic model. So with that, you guys have any questions? I'm going to stop sharing.